6. But what Chapter 6 is really kind of concerned about is looking at energy diagrams, the components of a reaction, kind of the general overview of what you would expect to see for ultimately the rest of this semester, and kind of pushing it further, the rest of next semester as well. Okay, so the end here is all about reactions. We're going to look at a couple different functional groups and then all the reactions possible for them. Second semester, you look at all the other functional groups and all the reactions that come from them. Okay, so there really isn't any more to discuss about structure or spectroscopy, but you have to understand that to apply a lot of the rules that show up, or a lot of the patterns that show up with the reactions. Okay, so if we look at the components of a reaction, in this case we've got an overall reaction showing up, a standard organic reaction. This is what you will be doing in the lab, actually, this exact experiment. So if we're going to go through and identify the parts of this, it might be helpful to know what we're talking about. What is the substrate? Any ideas? Where's the substrate in this reaction? It's definitely going to be on the reactant side. This guy is typically our substrate. It's usually what we're acting on, okay, what we're concerned about actually happening. So we'll keep referencing the substrate, particularly when it comes to substitution reactions. After that, it kind of falls out and we stop looking at referring to it as a substrate and look at it more as a reactant or a reagent. You will hear reactant and reagent pop up as well. Okay? Reactant, hopefully everybody understands, would be on the left side of the equation, on our reactant side. What's a reagent? Okay. The reactant is something that we would typically kind of equate with the substrate. Almost the same thing. But it's slightly different from the reagent. The reagent is what we're reacting our substrate with. Kind of an odd statement, because that means your reagent is also a reactant. Okay. Typically, your reactants are usually smaller. They're also typically inorganic. Okay. It just kind of depends on what you're trying to work with. Okay. So in this case, where's our reagent? Our reagent, typically see above the arrow, not always, but you'll typically see the reagent listed above the arrow. You'll notice that also in this case it is a reactant, or sorry, an organic compound as well. Remember, we kind of push towards that smaller section. Very often you'll see these terms used interchangeably, so don't put too much weight on deciding where everything is, but that's kind of the idea on where we can find these things. Next part of this is a catalyst. Where might we see the catalyst? Catalyst is typically shown under the reaction arrow. Okay, so we almost always see the catalyst underneath. Is whatever that's underneath the arrow always going to be the catalyst? No. Turns out silver nitrate, it's not really acting as a catalyst. It's more acting as a reagent in this reaction. So why is it put underneath the arrow? There was something else above the arrow. Okay? So organic is kind of obnoxious in that respect, that we aren't very consistent about where we put each of our species. Okay? This, or our silver nitrate, is an extra reagent that almost kind of acts as a catalyst in this case in terms of helping speed the reaction along for us, but it's not acting strictly as a catalyst. How might we know it's not acting strictly as a catalyst? It changed. The catalyst can neither be consumed nor produced. If we go through and take a look at our reactant of silver nitrate, or AgNO3, we would expect to see that show up the exact same on the product side. But if we go over to the products, we see silver chloride as a solid. So it definitely did change in the course of the reaction. So it didn't really act as a catalyst, but it is important to help this reaction go. Okay. Next one, solvent. Where do you typically see the solvent written? Solvents are typically tricky. Sometimes the solvents will show up underneath the arrow. Most cases, solvents aren't specified at all when we look at our overall reactions. Okay, why? No. How many of you work with solvents in this room? While in this room? The solvent very rarely actually gets worked with in the lecture, so in a lot of cases the role of the solvent is kind of minimized and we don't evaluate it as much when looking at reactions because we don't actually use the solvent all that much. When you shift into the lab, that's where it becomes more important and more relevant because you then actually get your hands on a solvent and use it. So solvent choice is really important. We will talk about it, but it very rarely shows up in a reaction scheme. If it does show up, where does it show up? Whoops. Usually shows up underneath the arrow. Is that always the case? No. Where else is our solvent in this reaction? Turns out our reagent, methanol, that's above the arrow is also acting as a solvent, not just a reagent. Okay. In this case, if we're going to use a solvent as a reactant, you typically see it show up as solvolysis, meaning solve for your solvent and lysis for your reaction. So if your solvent is involved in the reaction, you'll almost always see it written above the arrow, and it may or may not be directly implied as the solvent. Okay. It kind of depends. Reaction conditions. We're usually actually pretty consistent with our reaction conditions. Where are the reaction conditions typically listed? We could write STP, but we're really looking at temperature. Okay. We can bring pressure into it, but in most circumstances we don't want to deal with pressure, particularly higher pressures, because what do higher pressures tend to do? Explode. So we tend to avoid those types of reactions that generate high pressures. Okay? So we're really looking at just temperature when we're concerned about our reaction conditions. That information nearly always is again written underneath the arrow. Okay? Not always, okay? But nearly always that's where it'll show up. You can see it written as an exact degree Celsius temperature value. You might also see it written as a delta symbol. Okay, delta for a change in temperature. Okay. And at least one of these we're consistent on. Where's the product show up? Product is always on the right-hand side. Okay, but it wouldn't be organic unless we made it just a little bit more confusing. Anybody notice anything interesting about our reaction? It's not balanced. Okay? Most organic reactions are written not balanced. Why? Because whatever we didn't balance in there, we didn't care about. Okay, this is organic chemistry. If we drew out that other ion, we'd be looking at nitrate. What is the role of nitrate in this reaction? A spectator. So since I don't care about its presence, I don't write it. Okay? So you will very often see that kind of disappear. Is that the only thing that wasn't balanced in this reaction? You're also missing a hydrogen. Okay? H plus is actually kind of important. Okay? Is it important necessarily to our product? Not really. So again, we don't really show those products. Okay? I know balancing is something that was beaten into your head in general chemistry, and I will try my best to always balance the reactions that I put out there sort of within reason. Okay? Be aware that you may not see things balanced. One of the big reasons why we don't balance things within the lecture is that if we provide that extra piece, sometimes it can give you a really big clue to what happened in the reaction. And you can just kind of guess your way through the reaction without actually knowing what's going on. Okay, so a lot of times it won't be balanced because we don't want to give you that extra clue. Yes?
So does that mean if you go through and balance it, that you can do what you just said?
Yeah. But then the question is, how do you balance it? So where does the hydrogen ion go? Where does the nitrate go? So you could see secondary reactions that you may not be able to predict. But yes, identifying what things changed across the reaction is incredibly important. So you don't necessarily have to specify what piece it was, okay, or where it went, but what happened. Did it disappear? In this case, the loss of that hydrogen ion, how many people saw that? That hydrogen ion will become really, really important after exam 3. When we look, or sorry, it will be important for exam 3. Elimination reactions involve the removal of a hydrogen ion. That hydrogen ion is almost never shown in the product. It just disappears from the reaction. Okay? If you aren't careful and you don't see that hydrogen ion in predicting your products, you can end up getting the wrong thing. Okay? So make sure you look across a reaction, try and identify those pieces, and get a quick interpretation on it. Don't spend a lot of time on it, but get kind of a quick idea on what's happening within the reaction. Okay? Questions about what we got up here? Yeah?
What is the R?
Sorry?
What's the R stand?
Oh, good question. The R group usually refers to just carbon, and then something else after it. Okay? So what we're trying to do is add on some alkyl group that does not change the overall chemistry. So it won't be a hydrogen, typically, and it won't be, say, an oxygen or nitrogen or other heteroatom, because that's going to drastically change the chemistry about that central atom. Okay? So really what we're saying with that R group is that that can be anything. Doesn't matter. The chemistry is still going to hold true. Okay? Yes?
The hydrogen ion is still there, right?
It is still present in the solution, absolutely. We typically won't include it in our reaction because the hydrogen ion isn't in our product. Okay? Typically, when we look at our product for organic chemistry, we're really only referring to the organic product.
It's still there.
Okay, the hydrogen ion is still present, it's just not attached to our product, so we ignore it. Okay? Like I said, I will try my best, at least within lecture, to always balance the reactions. You will notice that I will miss pieces right and left. Okay? And those pieces will be these inorganic things that I just don't care about. Okay? Feel free to point it out and notice it whenever you see it. Other questions about what's up here? Okay. Oh, there we go. So our reactants and our reagents, that placement usually depends on our author's opinion. Okay? And that's kind of what we got for pretty much everything in the middle. Okay? All of these things really just kind of depend on whoever wrote the question and where they feel it should show up, if it should show up at all. Okay? And then the other big important part of this is your reactions are almost never balanced. So don't expect to see all of your products actually present. Components of a mechanism. So the mechanism is a little bit nicer, probably a little bit closer to what you might expect from general chemistry. Your mechanisms will always be balanced, and you will specify things in very particular orders and fashions to represent exactly what is happening within the reaction. Okay? Your reaction scheme, or what we just looked at, kind of that reaction, I don't know how to call it other than a reaction, looks at our overall image. Okay, so it doesn't care about individual steps, it just says overall, beginning, end, this is what we got. The mechanism actually goes through and looks at each individual piece and says, okay, this is what happened at this point in the reaction. At this point in the reaction, another thing came in and did this. At this point, another one came in and did this. You're going to be responsible for a lot of mechanisms. On exam 3, you will absolutely be expected to provide an entire and complete mechanism showing everything that occurs. You won't have to worry about that for the final exam because it's multiple choice, sort of. The one caveat, when we look at our mechanisms, what products we get is largely dependent on how the reaction occurred, what the mechanism was. So we can still ask a multiple choice question and give you 3 possible products. All of them, depending on which mechanism you used, would be valid. Okay? So you can still see mechanism type questions show up, you just won't have to worry about the arrow pushing, okay? Which is what we kind of talked about when we looked at resonance. Okay? One of the things that's nice about our mechanisms is everything is kind of standard. Our reactants are always shown. We won't see typically anything floating over arrows. Okay? It will always be, dang it, balanced, at least within that step of the reaction. Okay? So it's kind of nice in that respect. The one thing that's different, and this is where most people tend to get annoyed with mechanisms, is that we add some extra information to this. With the mechanism, what we were trying to explain is how the electrons moved. Remember, this is organic chemistry. All we care about are the electrons. So what we're going to do is add to our mechanism a sequence of curved arrows to explain the exact ways that those electrons shifted and moved through the reaction. Okay? So first off, how many steps are in the reaction shown? 2? How do you know there's 2 steps? 2 sets of equilibrium arrows. Okay? So sometimes it's straightforward. Where's our product? The far right. All products was an interesting idea. We have a reactant over here, so I wouldn't take that to a product. But if we take a look at our first step, we produce something. That produced thing we could call a product. And I'm going to put that product in nice little air quotes, because it's been an air quote day so far. It's not really a product because we didn't isolate that at the end. That wasn't our target compound. What that was a product of the first step that allowed us to then continue forwards, which means it's not really a product, it's an intermediate. Okay? So every mechanism is going to have a reactant, it will have a product, and it may have an intermediate. It may not have an intermediate. It may have a whole bunch of intermediates. When we hit second semester, you can hit mechanisms that have 8 or 9 steps. You'd be responsible for each and every single one of those 8 or 9 steps and doing them in the correct order. Okay, that's a lot of work. How many steps are we looking at this semester? 2. Occasionally we'll hit 3. Okay? So we'll keep it relatively short and sweet when we look at our mechanisms. That's not really our choice. That's just how the reactions worked. Okay? So what happened with our electrons? What happened in that first step? What changed? Okay? You'll notice that we broke a bond between the carbon and the bromine. Okay? That disappeared. Where did the electrons in that bond go? How do you know they went to the bromine? Bromine started at what charge? Neutral, and it ends with negative, which means it had to gain electrons. There is nothing else shown as a reactant there, which means those electrons have to come from somewhere within that structure. The only thing that has changed is that bond. So we're going to take the electrons in that bond and we're going to put them where? On the bromine. So our arrow is going to say where our electrons started, the bond, and the electrons moved to the bromine. There's our arrow pushing. When it comes to a mechanism that you would draw out, it is virtually impossible to grade where you started the arrow. Okay? This would be the official correct answers we've got drawn there. But you could probably draw something like that just as easily. Well, where did that arrow start? Okay, in this case, that looked like it started from the carbon. If you put that as an answer on your exam and I took off points, would you get upset? Yeah, you'd probably come back and say, no, that's coming from the bond. Way too difficult for me to interpret. This is one of the huge advantages of sapling. Sapling will give you the option of starting your arrow in the bond or at an atom. If the electrons are on the bond, where does your arrow need to start? In the bond. So you have to be very, very careful when dealing with mechanisms to show exactly where the electrons started and where they ended. Sometimes sapling is nice and won't allow you to do other options. Okay, so be aware of that. We have to be very careful with our arrow pushing, always start where the electrons exist and move to where they need to be at the end. So what we just explained here was the bromine becoming positive. Okay, well, how did the bromine become, negative? How did the bromine become negative?
Reduce the electron.
It took electrons from where? That bond. Where did the electrons come from originally to make that bond? One came from the carbon, one came from the bromine. In showing this arrow, we used a double-headed arrow, meaning we moved 2 electrons. Both of those electrons are now on the bromine, which means what happened to the carbon? It lost an electron. How would I prove that in my mechanism? Well, the product I would draw would have what on the carbon? A positive charge to represent that it lost those electrons. Can I ever just assume that positive charge is there? No, why not? Goes all the way back to our rules and simplifications way back at the beginning of the semester. Because we imply hydrogens, we cannot imply formal charge. You have to specify it. Okay. We're now at our intermediate stage. You'll notice in this intermediate stage that I've brought in another species, okay, the cyano group. Okay. Why can't I just bring that in now?
Because you want to.
Kind of along the lines of because I want to. It's now a new reactant. Why did I not show it earlier in the mechanism? Because it didn't do anything. I don't care about it until it actually can do something. So you may see things pop up in a mechanism partway through because they needed to be there to push the rest of the reaction. And they didn't need to be there earlier because they didn't do anything. Okay? So if we look at our intermediate, is it stable? Can the bromine hold a negative charge?
Yeah.
Why can bromine hold a negative charge? 2 reasons.
Because it's unloaded.
Because what?
Or because it's got a full octet of
I won't accept an octet explanation. That's not a bad idea.
Okay, it's got a full shell.
That's still the octet. It's electronegative, so where you were going with halogens would encompass both answers. It's electronegative, so it's going to hold electrons pretty well. And what was your analysis? Because of it's not quite weight, but right idea, it's its size. It's so big that I can push that extra electron over a very large area, which does what to the stability of that negative charge? Stabilizes it. So bromide is actually relatively stable as a negative charge. Turns out most of our halogens are pretty stable as being negative. The one exception, fluoride, because it's ridiculously small. It can't hold those electrons very well. Okay? So bromide's fine. How about the carbon? We're looking at something that's relatively small, okay, and charged. Small and charged is not a particularly good thing. Do we have a way to stabilize that carbocation? What's that? Form a bond. Good answer. How can we form that bond?
Sharing electrons.
We could go through and just push exactly what our mechanism shows. What does our mechanism show as the result of this step? The carbon of our cyanide forms a bond with the carbon of our ring. How would we show that mechanistically? Where did the electrons start? Why did they start on the cyanide? How did you know they started there? Because it's negative charge. And to be negatively charged, it must extra electrons. Could I ever have that positive charge share electrons? Why not? It's missing electrons. Okay? These kind of relatively simple statements, which you guys are all doing great with, by the way, thank you, okay, are really, really important to remember whenever you're going through and working with these mechanisms and trying to predict things. Okay? If you can maintain these rules, you can actually start to predict how reactions are going to work before you even see that reaction mechanism drawn out for you. Okay? So it is an important tool to take advantage of.
Then how would you know that the cyanide replaces Br?
I was just going to say the same thing.
So let's finish our arrow first. Okay. Where's our arrow going to start?
The electrons and cyanide.
The electrons on the cyanide. So like this.
Probably.
No, the negative.
Where the extra electrons are at the negative.
So I want to push away from the negative, because the negative just implies that there's extra electrons. With that structure, there's extra electrons on the nitrogen and there's extra electrons on the carbon.
But the carbon's the one that's gonna share the bond.
Why does the carbon share the electrons? You're right. Less electronegative, which means
It doesn't hold on to its electrons.
it can't stabilize the electrons as well as the nitrogen. So when we look at the cyanide, which is more nucleophilic, which one's more willing to share those electrons? Carbon, not the nitrogen. How else do we know it's carbon?
Oh, because
Look at the product, and in the product, what happened in the product? The bond is formed between the carbon and the carbon, not between the nitrogen. Okay? So take advantage of the information that's given to you. Okay, so you guys asked a good question. How do we know the cyanide would actually react? Okay. Well, in the course of this reaction, really what we're evaluating is the stability of Br minus versus the stability of cyanide. Why would we be evaluating that difference? The first step of this reaction, what happens? Bromide comes off. And the second step, if a reaction is going to occur, what has to happen? The cyanide must attack, not the bromide. If that's going to be the case, what are we saying about cyanide? It's more reactive because it's less stable. Why is it less stable than the bromide? Carbon is smaller and less electronegative. Okay? So we can start to predict things about how a reaction is going to occur by looking at the most unstable species present and saying, if I do this reaction, does it give me something more stable or less stable? If it pushes to something more stable, that's probably a good option, and we should push our reaction that direction. Okay? Yeah.
So then what, at the very beginning, what caused the BR to break off anyways?
Good question. Why would the bromide break off to begin with?
Did you put it in a solvent?
Okay, so the solvent can help with that. Okay, bromide is stable on its own, but for it to leave, this carbon structure must be stable. If that carbon structure is so unstable that it cannot form, does the bromide ever come off? No. So what we also need to be able to evaluate is that positively charged species. How stable is that positively charged species? We said it was reactive as far as our reaction going on. Okay? But now what we want to do is predict, is it even stable enough to form? Okay? How do we know it's stable enough to form? What would we look for? And sorry, that looks too messy. I'm going to redraw it. First step might be to classify the cation. What type of cation have we formed? Carbocation, true, I can accept that. Talked about it briefly in mass spec. It's going to become really important for this particular type of mechanism.
+1.
How many carbons are attached to our carbon? 2 carbons. That is a secondary carbocation. In the scheme that we've talked about, how stable are our secondary carbocations? They're not the best, but they're also not the worst. So they're somewhere in the middle, so this is possible. We could possibly form this carbocation. Is there something else to suggest that this carbocation is actually indeed more stable than just a secondary? Yeah, say that a little bit louder. I think I heard you say it. Resonance. We can move the electrons of that pi bond over to that position. In that case, what happened? Our carbon, our carbocation, accepted an electron. It started positive and it gains an electron. What charge is it now? Neutral. So cool. Our red carbon, which I have to go through and mark again, is now neutral. We stabilized it. Good job. What else had to happen? Another carbon had to lose an electron. Which carbon lost the electron? One to the left. All the carbons are to the left, though. So that is a valid answer, but I want a little bit more. We got 1, 2,
two.
3, and 4.
Oh, okay, number 2.
What happened to carbon number 1?
That's the same number of.
We had 1 electron sitting on the left side. What did we do with that 1 electron? We just moved it to the right-hand side. It's still associated with that carbon. So it neither gained nor lost an electron. What happened to carbon number 2?
Still off.
We took an electron in that pi bond and we picked it up and we put it over with our other carbon, our carbocation. It lost an electron. That carbon is now positively charged. We have a new positive charge. How stable is this positive charge? How would we classify it? Secondary. Hey, cool. So we got the same kind of stability. Could we do resonance with this one?
Yes.
Yep. What resonance would I, or where would I start my arrow? Top pi bond or bottom pi bond? Why the bottom, not the top?
Because the positive charge.
The top one we already moved. If we move the top one back, where are we going? Right back to where we started. So let's pick a different pi bond. We could pick the bottom pi bond. And we could now draw that structure, going through that same reasoning. So we find our source of electrons and we move it to where our electrons are lacking and we continue to propagate through. Okay? How many resonance structures should you end up with this guy? Pretty sure there's 5 structures. Okay? So as you continue to move the pi bonds, you should notice that your cation is going to eventually make it to each and every single carbon. Okay? Questions? You guys sure asked a lot of mechanism questions on something that wasn't supposed to be a mechanism yet. So good job. You're thinking ahead. I like it. So within our arrows, we're going to have a whole bunch of new arrows popping up. We've got our standard reaction arrows. We will have equilibrium arrows, which won't be as relevant for the final, but we will talk about equilibrium reactions both in lab and in lecture because they are important to watch out for. The double-headed arrow is only used between resonance structures, so don't attempt to say that means it's going forwards and backwards. That is purely for resonance. The full-headed curved arrow means we're moving 2 electrons. Okay, so everything we've done so far is moving those 2. We could potentially move just 1 electron. That ends up being a half-headed arrow, usually referred to as a fishhook. Okay? You will be seeing both of these by exam 3. Okay? So make sure you know when to use the arrows and how to use them. Where do your curved arrows start?
Where the electrons are coming
Where the electrons are located. And where do they end?
Where they went.
Where they went. Okay? So our rules of our mechanisms, our curved arrows will always start at a source and end someplace where we're lacking electrons. Those sources can be bonds or lone pairs. What type of bond? We should be more specific with that. No, I can't be more specific with that. I lied. That curved arrow can start at any bond, any type of bond, when looking at a mechanism. Focus only on moving the electrons. This becomes exceedingly tricky because what do you typically see in the course of a reaction? The atoms appear to have changed locations. The only reason the atoms change locations is because the electrons change locations. So when you look at a reaction, you don't look at the atoms, you need to look at where the electrons are located. You know those kind of electron map kind of drawings they provide in the textbook where you got red areas for high electron density and blue or purple for low areas? No? Okay, well keep your eye out for that. Okay, that's how you should be evaluating your structures. We will see a couple of those when we look at our overall deals. Okay? Electrons are very, very unstable. They have very particular moving patterns. We can only move them from an atom to a bond or from a bond to an atom. Okay, so be aware of that. When dealing with resonance, we have one extra bond motion. What's that bond motion? Or electron motion? We can move bond to bond. When we're dealing with mechanisms, focus on just these two. Resonance can do that extra bond-to-bond shift, okay, which is ultimately just the combination of steps 1 and 2. Okay, or rather 2 than 1. So, let's give you a little bit of practice here. Add curved arrows to the reactions shown. Yeah. So, if you got questions, it's nice. I did it in reverse order of difficulty. That was intelligent. So that last one, we're just taking the electrons from that carbon-chlorine bond, and we're putting them on the chlorine. The result is that we end up with a positive carbon and a negative chlorine. You'll notice, how many electrons does the chloride have at the end? 8 electrons. Where are those 8 electrons? Remember in those organic simplifications that I talked about at the beginning of the semester? Halogens often have implied electrons. Okay. In this case, our halogen does have implied electrons to it. Okay. Be aware that you will see these. I think this one is actually copied and pasted, because I think when I put on my charges, mine have circles on them. Okay. So those electrons are present. They are present in our starting material too. Okay, so remember those. We're going to work bottom to top. The second one. What happened? Okay, we broke a bond. So I like looking at that. So you're saying we broke the carbon, or sorry, we broke which bond? The carbon and iodide bond. Where did the electrons in that bond go? They went to the iodide. And that's how we ended up with the negatively charged iodide. Do we have a positively charged carbon? Do we have a positively charged carbon in this mechanism?
They don't show us.
No. Why do they not show that step? Because it happens at the same time. We never form the positively charged carbon. How can we avoid that step? What else has to happen? We're going to have to form the bond between the carbon and the oxygen. Where does our arrow start? With the oxygen. Why the oxygen? It's where our electrons are. Those electrons, sorry, can't see my screen, attack, shoot. Where? The carbon. So we will take those electrons directly to the carbon atom, because that is where the bond is forming in the case of this reaction. Okay? And now what we have is the arrows and the products to prove that that's exactly what happened. Okay? Questions about those bottom two? Okay, how about the top?
What's the dot in the product on the top? Is that a plus?
That dot is a single electron. Okay? Which means the arrows that we need to use are going to be our fish hooks. Okay? If we go through and take a look at our reactant, you'll notice that that chlorine has how many electrons around it? 7. It has 1 unpaired electron. Okay? If we go through and look at the product, what's that dot? It's 1 unpaired electron associated with the carbon. Okay? This one I think I actually drew, so I should have done a little bit better here. Let's change that HCl now to actually what that's going to show. H bond Cl. So what things happened in this reaction? The hydrogen bond broke to the carbon. How did it break? So let's take a look at the electrons. We've got the electrons in that bond. The hydrogen took 1 electron. Okay, and I'm going to float that off into space here for the moment, and we'll talk about that in a second. What happened to the other electron in that bond? It went to the carbon. I have to specify it. Otherwise, I'm saying that electron is still in a bond. It's not in a bond. It can't physically be in a bond because there's no other electron. So we also have to add an arrow saying that the electron went to our carbon. Okay? So for that single bond breaking, we have to specify 2 arrows, because we have to account for the motion of both electrons. Is that the only thing that happened in this reaction?
Nope.
What else happened? The chlorine and the hydrogen formed a bond. How do we make a bond?
2 electrons.
We need 2 electrons. Where are those 2 electrons?
One from the chlorine,
One from the hydrogen that we threw out into free space, and
one from the chlorine.
the one unbound from our chlorine. This is the proper arrow motion. You'll notice, where are the electrons between the hydrogen and the chlorine going?
To each other.
They're kind of floating out into the middle of nowhere, which seems a bit odd. Okay, we can't take the electron from our hydrogen and put it on the chlorine, because then we aren't saying we're forming a bond. We're having hydrogen give 1 electron to a chlorine. Well, that doesn't make sense. Chlorine also has to contribute an electron back to the hydrogen. So what we're going to do in the case of this type of mechanism with our fish hooks is we're going to show the bond formation actually forming where we would predict it to form, which is the space between the atoms. Okay? We can't do that with our other mechanisms, with our 2 electrons, because if I drew that arrow into the space, what's the space to? Is it to the carbon or is it to something else? It's ambiguous. We can't figure it out. So moving with 2 electrons, we'll go from our atom to our bond, or sorry, our atoms to form a bond. When we're looking at moving a single electron to make a bond, we'll move them to the space of making that bond. Okay? Bit kind of tricky to deal with. Questions about that? Okay. We have 2 different mechanisms explaining what's going on here, which means we need to come up with 2 different names for these. Okay? Our bonds broke in a different fashion. Okay? What's that fashion? In our first example, our electrons went back to their parent atoms. So the electrons took, or went back to their parent atoms. The atoms took their single electron back. What type of bond cleavage was that? So we can go with lytic, because we're looking at breaking the bond. It's homolytic. They went back to their exact same starting points. In the other circumstances, what happened? We still broke the bonds, but the electrons went only to one source, one side. So we have heterolytic. Okay? We will make reference to each of these as we go through our individual chemistries. What you will find is I have a preference for the heterolytic reactions because I can evaluate their stabilities much better. I can look at a negative charge, I can look at a positive charge, and I can evaluate those. I understand how those work. Where's a positive charge going to go? To a negative. Where's a negative charge going to go? To a positive. There is no kind of weird area in between where I can do anything. Okay? The positive must go to the negative. What happens in the case of the homolytic cleavage? Where does our single electron go? Anywhere it freaking wants. Okay? There are some rules to it, but they're very limited. So if anybody asks you to predict a mechanism to try and make some compound, make it a hetero or a homolytic cleavage, because you can break any bond you want, and you can pretty much produce anything you want from those. Your yield may be horrible, but that's not what they asked. Okay? The homolytic cleavage is typically referred to as a radical reaction or a free radical reaction. All right, so when people are talking about free radicals in your body, what are we looking at? A single electron, typically on oxygen. It's usually oxygen free radicals. Yeah?
On sapling, they let them move that electron into space and meet up? Have those kind of questions on there.
Good question. I don't remember seeing those mechanism questions. That's actually a really good question. I don't know how sapling's going to set that up.
Okay.
I did go through and do all the problems, and I don't remember seeing a mechanism per se with the free radicals, so I don't think you'll see it. Questions? Okay. So we get these 2 types of cleavages, your homolytic and your heterolytic. We have to make sure that we can classify these accordingly. because that's going to determine what mechanism we're working with and potentially what reagents we're going to work with. Bond breaking will always require energy, which means that type of reaction will be endothermic. It has to absorb that energy to break that bond. Bond forming always releases energy, so that type of reaction is always exothermic. Okay? Do I actually need to write that up there?
Yeah.
No? Okay. So, energy diagrams. What we've got here is kind of a summary of everything. In my opinion, this slide right here actually summarizes everything that you learned in 152. Okay? All put up there very succinctly in one big giant picture. Okay? You are responsible for interpreting each of these individual systems. You'll notice that one thing that I definitely left off of this would be the x-coordinate, which is typically written as the reaction coordinate. Okay? I'll always abbreviate it RxN. Where are your reactants? Where are the reactants in the energy diagram? R for reactant, which is typically found on the left-hand side, just like an overall reaction. Products, P on our right-hand side. Okay. Where's the intermediate?
Transition.
There isn't an intermediate. For there to be an intermediate, we actually have to have a well. We have to have some place for that species to exist. When we look at an energy diagram, as you shift around, what's happening at the transition state is the point when you change from being reactant to your product. Okay? There isn't an intermediate species there. And in fact, the transition state never really exists. It's something that we theorize on shifting immediately from our reactant towards our products. We can pretend to draw transition state structures so that we can try and understand something about how that reaction is working, but it is not an intermediate. How would we see an intermediate? We would need 2 steps. We'd have to have a well. What could we put in there for our intermediate? I. Good. Everybody's on the same page. Okay. To form an intermediate, how many steps must there be in a reaction? We have to have at least 2. What if we have 3 steps? We have another well, which means another intermediate. Okay. Other important things to address. Okay. We've got thermodynamics and kinetics. Thermodynamics is concerned about the energy between your reactant and potentially your intermediate. Okay? But it's ultimately looking at the energy difference between reactants and products. That is the only thing it's concerned about. Does that tell you anything about how fast the reaction goes? No, it just tells you about how much energy is released. In this case, is this an exo or endothermic reaction? Exothermic because it ends at a lower energy than we started. We have to release that energy out into the system with heat, so we've got an exothermic reaction. What would the sign be on our delta G? Product minus reactant, final minus initial for our delta. If our product energy is smaller than our reactant energy, what happens? We get a negative. So our negative is our exothermic reaction. And again, it says nothing about the speed of the reaction. Yes?
Why does the energy start higher and go down and then just go back up? Like where it very first starts for the reactants, the energy decreases?
When you look at energy diagrams, you have to realize everything is existing in a well. Okay, this isn't just a 2-dimensional slice. This is a 3-dimensional slice of the overall species. That species can exist at varying energy levels. That energy level does not necessarily mean that it goes only to this product. There could be other products that it goes out towards. So when we look at these, we should be drawing wells, not plateaus or flat lines, because it's existing in that energy state. Okay? And depending on what's happening, it could potentially go some other direction. Okay, so that's why I'll always draw it with that well, or always try to draw it with that well. You'll notice that most textbooks don't show it in a well. That's fine. Okay? Well is technically more correct. Okay? Anybody know the thermodynamics of combustion? Exo or endothermic reaction? Exo, what are we doing as we exhale? Combusting. We are all combusting right now. Okay? And it is a spontaneous combustion. Why are we still here? Spontaneous and our exothermic says nothing about the rate at which we combust. What determines the rate at which we combust?
Activity.
Energy of activation.
Our energy of activation. For us as humans, what's our energy of activation for a combustion reaction? Really, really high, which means we don't combust very quickly. Okay? Speed is all determined on the height of that transition state. If we have a transition state energy that is incredibly high, that means that reaction will not go quickly because we have to overcome this energy barrier before we can actually form the products. When we take a look at the two curves drawn on here, the black nice-looking one or the red gimpy-looking one, which one occurs faster? The red gimpy one. Why?
Requires less energy of activation.
If we look at the barrier for the reaction to occur, it is much less than it is for the black one. Okay? So that reaction is going to occur much quicker than the first one. What if we went through and changed this a little bit? Let's actually say, actually we can do it this way. Which is going to occur faster? Reactant to intermediate or reactant to product? Reactant to the intermediate. Again, we're just looking at the activation barrier. You'll notice, is that an exothermic or endothermic reaction? It's endothermic. We had to put energy in to get everything up to that intermediate energy level. Okay? Even though our reaction is now non-spontaneous, it's still going to happen faster than our spontaneous reaction going all the way to the products. Okay? So realize you're looking at two separate stages here. You've got the kinetic side, which is just about the activation barrier and the relationship to the transition state. And then you also have the bottom section, our thermodynamics. So you can look at an exothermic reaction, which is going to mean what? Releases energy. What would you see in your energy diagram? The product energy needs to be lower than our reactant energy. What if it's a slow exothermic reaction? It's going to have a tall transition state, but the product energy is still going to be lower than our reactants. Okay? So we can vary those two things independent of each other depending on what circumstances we're looking at. Okay? Questions about that?
Part of us is combustion again.
All the organic stuff, everything with carbon. So when we're looking at how fast a reaction will occur, it doesn't tell us anything about how much it produces. It just says that we get there fast. Okay, what's going to tell us how much we produce? Come back to that one. So when we look at kinetics, again, it's how fast. So what's going to control the speed of the reaction? What's that? We could look at catalysts, but that's adding a secondary thing. Our activation barrier, so our activation energy. How can we calculate the activation energy? Yeah, I know you guys have those all memorized, right? Your Arrhenius expression. Your Arrhenius expression on the far right can give you your activation energy, or the relationship between your activation energy and K. This K is the what constant? The rate constant. How do we solve for K? Not products over reactants. Products over reactants is the equilibrium constant, not our rate constant. Our rate constant is determined by looking at our rate with respect to the concentrations of our reactants, okay, to their particular orders. Okay, everybody's favorite section of kinetics. Okay, typically you see an M or an N up there. How would we determine those orders? You have to determine it experimentally. Okay, so we can go through and do all that. We're not going to do all that. Okay. So all of this information is really manifested in the rate determining step. So if you really think back to 152, you guys did stuff with mechanisms. So which of these is a plausible mechanism by looking at the rates and making sure it matched your overall rate expression. There's all sorts of fun and dandiness. Okay? And all of it hinged on that slow step. When we're looking at our reactions, particularly in the substitution cases, we're going to be looking for that slow step to determine what's going on with our rate. Why is that going to be important? Well, if in my rate limiting step, the nucleophile is not involved, do I care about the strength of the nucleophile when trying to set up that reaction? No, because it's not involved in the slow step. It's involved somewhere else, and that somewhere else is irrelevant because all I'm concerned about is speeding that slow step. Why would we want to speed the slow step?
So you're not step 2 goes faster.
So step 2 goes faster. What was your statement? One of you guys had something?
Not make it slow anymore.
Not make it slow. Why do we not want to make it slow? Come on.
Higher yield.
No.
Less time in lab.
You can get out of lab faster. So if we understand the reaction, we can change certain components within our reaction to make it go faster so that we don't have to be in lab for as long. Or if there's nothing we can do to make it go faster, what can we do? We can set up the reaction and we can leave. Go to the bar, get lunch, get dinner, come back 24 hours later. Oh, did my reaction finish? Yeah, it's done. Now I can continue forward. So if we have some understanding of how fast the reaction can go, perhaps we can change it. And if we can't change it, we can accept it and let it do its own thing and come back later. Okay? Power to organic chemistry. Talk to any biochemist, they aren't going to be able to do that. They have to spend the whole time in lab. Okay? So how can we control the rate? Change the height of that activation barrier. How can we change the height of the activation barrier? We could add a catalyst. What else could we do? We could heat it up. What does heating it up do?
Increase the
It's going to increase the kinetic energy, effectively taking our reactants, and this is effective, so it's not really true, but it's kind of close. It takes the energy of our reactants, and instead of being nice and low, if we heat it up, we can get their overall energy a little bit higher. What happens to the effective activation barrier? It gets less. Okay? Heat does not change that as far as how we look at our energy diagrams. We're concerned about the raw energy. We don't look at temperature effects on that raw energy. Okay? But we can speed it by increasing the kinetic energy of our reactants so that they effectively shift to a higher energy. What's the problem with adding heat? It increases or it decreases the activation energy for every single possible reaction. If there is more than one thing that can possibly happen within your reaction, there is. Okay? You're going to increase those as well. Okay? So we want to be careful with adjusting our reactions with heat because just adding heat could actually ruin our reaction or ruin our yields. Okay? I'm not sure what I was doing with that. The next part of this, we could look at our thermodynamics. Thermodynamics is going to measure the extent of the reaction. Okay, so how much product is formed. So we could make a really fast reaction. That could be an awesome idea. We got a super fast reaction. But what's the issue with the reaction? No. Yield. We could have a really fast reaction that is massively endothermic. So I could look at a, whoops. You didn't see that. We could have a reaction that has a very low activation barrier, okay, but then the product, well, man, that doesn't work very well. It's hard to draw that. Very low activation barrier, but our product energy is very, very high. So we may be able to get there relatively fast, okay, but our product are so shifted, okay, to disfavor the product formation that we don't get a very high yield. Okay? So the speed of the reaction can help us get there faster, but if we don't produce any products, it's a pretty useless reaction. So to figure out how much products we've determined or made, that's where we would shift into the equilibrium constant. Okay? That was your products over reactants. Why does everybody get confused with the equilibrium constant? It's the same letter, just different case. We're looking at a capital K, products over reactants. This is related ultimately back to our free energy. That's where we get in delta G's and all that fun stuff. So you could go through and calculate a lot of these different things. One of the things that you'll notice when you look at a lot of energy diagrams is more often than not, what they show as the difference between the I'm going to do it again. What they show as the difference between our reactants and our product energies, what do they typically show as your delta in there? It's usually delta. You might see it as H, which from 152 you should all be freaking out and saying that's not a delta H, it's a delta G. Why can we get away with saying it's a delta H? Typically, in most reactions, the change in entropy is tiny. So that we can end up saying that the difference between our reactant and products ends up being our delta H. Okay? We can then use this, as the textbook goes through and uses, to calculate a bunch of differences in energy to determine if a product or a reaction is spontaneous or non-spontaneous by looking at the sign, be it negative or positive. Okay? Feel free to go through and do those calculations. I'm not going to expect you to go through and do that. When we talk about reactions, we will look at an entropic effect. What is entropy? It's a measure of disorder. It's the standard definition. The definition I like to work with instead is the measure of motion. The more motion, the higher entropy. Why do I not like disorder? Dis is a negative. Okay? So if you start bringing in negatives into it, it can confuse things. So I like to stick with the positive. If we increase motion, we increase entropy. Okay? Makes a little bit more sense, at least to me. What happens if your equilibrium constant is greater than 1? You get more products, which would mean what is the sign on your delta G? It's negative. Way to change it up, switch in the other answer. It's negative. It's a spontaneous reaction. Okay? So if you have a large equilibrium constant, your delta G ends up coming out as negative. Okay? How could you go through and test that? You're allowed a calculator. You could always take that expression, take the natural log of a really big number and see what happens to the sign. Okay? Punch it in and see what happens. What if your equilibrium constant is less than 1? You're going to have a positive value. Your product concentration is smaller than your reactants. What happens if your equilibrium constant equals 1? Okay, the concentration of products and the concentration of reactants are the same, and your Gibbs free energy is 0. There is no favoring. What if K equals 0? That means there's absolutely no product formation, which would mean can't take the natural log of 0. If we can't form any products, is our reaction spontaneous?
No.
No. Okay.
So would it
So
just be
we
NR,
wouldn't
no
really,
reaction?
we would get no, or NR, yes, no reaction. So we wouldn't really be able to apply that last one. Okay, it just doesn't really make sense. Questions about any of that? Okay, that's kind of the level of interpretation that I expect out of looking at your energies, your equilibrium constants. Still got 5. Okay, 5 is actually pretty sizable too. Okay. Questions? So you're all packing up, we'll say no. What arrow should be provided in the box? Good thing there's a box that didn't show up. Thank you. What arrow should show up in this red box? So what we would expect is a larger arrow towards our products. Why would we expect a larger arrow towards our product? Our largest substituent is in the equatorial position. We would expect that conformation to be dominant as far as our concentration goes. And we'd expect very little shifting towards our axial substituent. What should the size of K be?
Greater than 1. K should be greater than 1.
K, we're looking at greater than 1. Our product concentration is larger than our reactant concentration. What should the magnitude of delta G be?
Negative.
Negative, because it's a spontaneous reaction. Okay. This is kind of, again, an example of the level of detail that I would expect you to pull out of this. I don't want exact numbers. I want you to be able to decide which way should the reaction go. Okay? This was supposed to be a quiz, but we don't really have time. Yeah, we don't really have time. So,
Yeah, we don't have time, you're right.
let's see. Where are we? That's actually pretty good. I'm not going to discuss this. We do have time, so if you've got questions, you can ask questions about it. If you don't want to ask questions, you understand everything on there, and you can interpret all of those, then feel free to go ahead and take off. Okay?